All right, good morning, guys. So last time we spent the class deriving the heat equation, right? And I mentioned that this is a pervasive equation that we're going to use a lot during the first third of the class, namely for solving problems involving conduction. Okay, the heat equation, also known as the conduction equation or the diffusion equation, goes beyond just heat transfer into a wide variety of different engineering problems. So it's going to be one that you want to understand the origins of. Today, tomorrow, and really the rest of the week is going to be dedicated to solving the heat equation for a variety of common geometries. Okay, and sort of seeing how we wrangle this partial differential equation to get actual engineering results. So today and Wednesday, we're going to talk about the solutions to the heat equation in one dimension. We're going to get into solving it in different coordinate systems, so doing things like solving for the temperature variation across the walls of pipes carrying hot fluids. And we're going to work that into what's known as resistance networks, or R values. So this is a concept that you see a lot if you go to Home Depot and you see sheets of rigid insulation that are rated with some particular R value. That comes directly from the theories that we're talking about in this chapter. Okay, so without further ado, today, as I said, it's going to be example-based. We're going to be looking at three and a half kind of different configurations of what's known as the plane wall. Okay. First, we're going to talk about one with fixed temperature boundaries, one with convective cooling, and with insulation on one face, and then finally a plane wall with heat generation inside of it. These first two, right? These are going to differ from one another in the way we apply boundary conditions, which is something we talked about in the last lecture and we'll put into practice today. And this last one is going to change in which version of the heat equation we're actually solving. So, one-dimensional heat transfer. First, let's be clear what we mean by one-dimensional. All right. 1D heat transfer pertains to the case where we're going to go ahead and say that the temperature variation is appreciable in only one coordinate direction. Oops. Okay, and I use the word appreciable, right? Because this is where we're going to have to use our sort of engineering intuition. Generally, this is going to occur, for example, if you have something like the conduction problems we were solving earlier. You say you have a bar, it's one temperature on one end, a different temperature on the other, and everything else is well insulated so that every cross-section has a constant temperature, right? If you set up an X, Y, Z coordinate system in that, assuming you orient your coordinate system correctly, the idea is that it only varies along the length of the bar. Let's say that's your X coordinate. Other examples where one-dimensional analysis generally works pretty well is if you have some sort of system where the temperature variation in one direction is just a lot larger than the variation in any other. So if you consider the walls of a building, right, the idea is generally inside of a room you're going to have a fairly consistent temperature across the surface of the wall. Maybe on the other side of that wall, here in Iowa, it's generally going to be a lot colder this time of year. And so if you were to put your coordinate system on the wall, let's say you were to say X goes through the wall, Y up, and Z your left hand. The idea is that the variation in y and z is going to be minimal compared to that dramatic jump in temperatures along x. So we just say, forget about the variation in y and z. The one that's really dominant here is the variation in x. Okay, so these are one-dimensional analysis is typical of, as I said, walls, as well as things like cylindrical pipes, okay, and spherical shells. So these are cases we're going to talk about when we get into the cylindrical and spherical coordinate systems. All right. So remember, I just want to quickly review, how do we write out the heat equation? You know, what was the final end game of the last lecture? We arrived at this expression that said, in Cartesian coordinates, right, rho c is equal to v k t plus q dot. All right, and then we said for most systems that we're considering, we can assume that K, our thermal conductivity, right, this is our mass density, this is our specific heat capacity. K here is our thermal conductivity, temperature is T, and Q dot is our volumetric rate of heat generation, okay, from things like nuclear, exothermic chemical, or electrical, right, heating. If we assume that K is homogeneous, that is constant throughout the domain of whatever we're considering, then we can go ahead and expand this out as rho c is equal to K d squared T dx squared plus partial T partial y squared plus partial c squared plus q dot. Okay. Three-dimensional heat equation. All right. So what we're really going to be doing today and for this week are two things. First is looking at these different types of problems. Okay, lining up the assumptions that we've been that we can make about the problems, and seeing how we can simplify this down to something easier to solve. And then the second thing we're going to be exploring is how, once we solve this, the different boundary conditions that we can specify are going to define how we solve for our unknown constants of integration. So methodology in general is going to be, first, list assumptions. Second, determine which version or what simplified version of the heat equation we get to work with. Three is going to be solve that resulting differential equation to find the general solution, right? A general solution is one that doesn't yet have any constraints on those unknown constants of integration. Fourth is going to be constrain those constants by applying boundary conditions, and then if we're considering heat flux or heat rate, right, out of step 4, you're going to get the temperature distribution and then apply Fourier's law to relate that temperature distribution back to a heat flux. All right, enough big picture stuff. Let's start into familiar territory. This is the one we sort of dashed through at the end of last lecture. We'll cover it again briefly right now. But this is the case of a plane wall. Okay, so over here on the right, we've got some warm region, some cold region, separated by a homogeneous wall. So by homogeneous, I mean that it's got a constant conductivity K throughout. The surfaces, in this case, have known uniform temperatures. So everywhere on this surface, it's at TS1. Everywhere on this surface, at TS2. Right? And we're specifying that there's no heat generation inside the wall, okay, and that the whole system is at steady state. And then it's implied here, I didn't write it out, but that we're working the system that is one-dimensional That is that the temperature varies only along the x direction. Okay. So we're trying to find the heat distribution in the wall. And before, as I said, we already did this. We wrote out rho c T equal to k squared squared plus T dz squared plus. There's our general form of the heat equation. And we can sort of systematically eliminate terms by looking at our list of assumptions here, or given the bullet-pointed givens. So let's start out with the idea that there's no heat generation. Number 2, we'll say that it's steady state. Number 3, that it's one-dimensional. Okay, these are our 3 kind of assumptions that are going to drive the simplification of the heat equation. So from number 1, no heat generation inside the wall. It means we get to kill this term. Okay. That Q dot goes to 0. Number 2, steady state. That means our time derivatives go to 0. And then number 3, that it's one-dimensional, so only has variations on x, means that all of these partial derivatives, right, with respect to coordinates other than x, also disappear. Which leaves us with k, a much simpler governing equation to solve. Okay. So carrying this over to the next slide, let's go ahead and write that out again. So here's the governing equation we ended up with. K d squared t dx squared equal to 0. Right? The general solution is found just by integrating this progressively once and twice. So integrating once gives us dt dx is equal to, in this case, right, c1. And then integrating again gives us t equal to c1x plus c2. Note, at this point, we haven't used any information about the boundaries. All right. So this is the general form of the solution anytime you have steady, one-dimensional heat conduction without heat generation. Right? Anytime you get to cancel out those different directions, that time derivative and that Q dot term, here's what you end up with. Linear temperature distribution. The question is, what are these constants going to be, and how does that fit in with our T1 and T2s that are specified on the boundaries? So applying boundary conditions next, this is where this general solution becomes a particular one. At x equals 0, we've got the t's equal to t1. So c1 times 0 plus c2, okay, is equal to t1, or rather ts1, which tells us that c2 is equal to ts1. And then at x equals L, right, we've got that T is equal to TS2. So plugging that into our general equation, or general solution here, we end up with C1 times L plus TS1 is equal to TS2, which leads to C1 equal to TS2 minus TS1 all over L. So finally, if we've solved for our unknown constants. Plugging those in gives us our particular solution, which is T is equal to TS2 minus TS1 over L times X plus TS1. So what this looks like is, as I mentioned, just a line connecting these two specified temperatures. So this is going to be the particular solution to any one-dimensional plane wall conduction, okay, that is steady, has no heat generation, and has specified temperature boundary conditions, which is not going to be, that's the simplest of all cases, right? This is what we came out with last time. What about the resulting heat rate and heat flux? Okay, so we established, right, that temperature distribution describes a linear decrease from TS1 to TS2. And we said the resulting temperature distribution was TS2 minus TS1 over XL plus TS1. So we can go ahead and find, right, the heat flux from Fourier's law. X is equal to, right, negative K T dx. There's Fourier's law. Plugging that in, we end up with negative K, in this case just TS2 minus TS1 over L. Okay, so this is the heat flux rate through, once again, any plane wall, steady plane wall, with no heat generation and known surface temperatures. Note that this is a constant. Okay? This is not varying on x. This is telling us is that if we go ahead and take the slope of this temperature distribution, multiply it by our thermal conductivity, and point it in, the opposite direction to the rate of increase, we're going to get a constant heat flux per surface, per unit surface area. If we wanted to then solve for the heat rate through, let's go ahead and say through the left surface of the wall, to be left, this would just be equal to Q prime X times A, or negative K A over L, TS2 minus TS1. So this is the cumulative rate at which thermal energy is crossing this boundary, right? It's just the the product of our heat flux and the surface area of that wall, or of the that face. What about the heat heading out through the right-hand side? Well, because the heat flux vector is constant, we're going to end up with Q right equal to Q double prime X times A, same thing, negative K A over L, TS2 minus TS1. Why am I going through this process? Well, because I want to demonstrate that if we were to, as a last sort of to beat this problem to death, if we were to draw a control volume around this section of wall, right, and we were to actually apply an energy balance, like we did in Chapter 1, the idea here is there's no mechanical work being done on it. There's no steady state, so the rate of stored energy, the rate of change of stored energy is 0. So what we end up with is just going to be a Q in minus Q out. Or rather, I should say that Q in minus Q out is going to give us the net change in the rate of stored energy. And in this case, Q in, right, is due to that Q left term, and the Q out is Q right. And because those two things are equal to one another, all it's really saying is that all the thermal energy crossing this boundary has to get pushed out this boundary. So that's the self-consistency of this steady conduction problem. So, yeah.
Would that always be the case?
It would not always be the case if you're talking about an unsteady conduction problem. If all of a sudden you were to change the temperature on one side of the wall, right, what you're going to end up with is potentially, let's say this warmed up a lot, your temperature distribution might look like this. It's not going to be linear anymore. So your heat flux vector, this guy, is not going to be constant at every cross section through the wall. And as a result, you're going to have more energy going in than going out until it gradually climbs back up to this linear distribution as it approaches steady state. Okay. But this transient heat conduction stuff is actually not something we're going to have to tackle until chapter 5. And it's a little bit, it involves actually solving the partial differential equation as a differential equation, because we have that time rate of change involved as well. Okay. So this is a pretty this is a pretty obvious conclusion we've come to. But it's a good sort of training wheels problem, because it shows us how to go ahead and simplify and constrain, or simplify the heat equation and constrain its solution using knowledge about the boundaries. Let's change it just a little bit. This time we have the same sort of setup with the wall. We say we know the temperature on this side, but over here we no longer know the surface temperature of the wall. We just know the surface temperature and the convective cooling coefficient of the fluid that's touching it. Right? This is probably a more practical problem in a lot of senses. So, for example, this might be, if you would imagine that this is a slice through the wall of a pipe. All right, maybe the pipe is carrying cold water. This is the outside of the pipe. Here's the inside of the pipe. You could attach a thermocouple to the outside and measure the surface temperature. But inside of the pipe, maybe you just know the temperature of the water flowing through it without actually physically attaching something to the inside of the pipe that's going to disrupt the flow. So in this case, right, we're going to have to call in some extra knowledge about the way heat is transferred through convection in order to solve for our unknown constants of integration. So once again, start off with, I haven't written it out, start off with our heat equation in 3 dimensions. This is the full shebang, and start canceling things out. So no heat generation inside wall, get rid of that. Steady state, get rid of that. And 1-dimensional, so we get rid of that. And we end up with, once again, okay, d squared t dx squared equal to 0. Okay. Same thing as last time. So the general solution, right, because we have the same governing equation, we're going to have the same general solution. So again, dt dx can be equal to c1, and t can be equal to c1x plus c2. All right, now let's start applying boundary conditions. Once again, we've got that at x equals 0, t is equal to ts1, right, which tells us that c2 is equal to ts1. This is where that new boundary condition is going to show up now, is that at x equals L, well, we don't know yet what the surface temperature is. We know what the temperature temperature of the fluid is. So what we're going to do here is apply the surface energy balance. And remember, surface energy balance is an energy balance with across a control volume that has no actual volume. In other words, Q in always has to equal Q out because there's no contained volume to store energy. So here we're going to say that Q, the heat rate due to conduction, has to equal the heat rate due to convection. Which makes sense, right? It's intuitive. The heat lost from the wall, or the heat that is crossing this boundary here from this side due to convection has to be dumped into the fluid via convection. So writing this out, we have for the conduction we've got Fourier's law, and over here we've got Newton's law of cooling. So write this out as negative K T dx is equal to, and then Newton's law says the convective cooling rate is H times Ts2 minus T infinity 2. All right, so go ahead and plug this expression here for dt dx. This is going to be, I should say, x equals L. And we end up with negative K times C1 is equal to H Ts2 minus T infinity 2. Which is equal to, and then we're also going to write from our first boundary condition. I'm going to try to get rid of this Ts2 and turn that into something that involves our unknown constants as well. So Ts2 we can get from essentially from constraining C2, right? Using this first boundary condition, we can say that what we know about the temperature distribution now is that T is equal to C1x plus Ts1. And so Ts2 must be C1L plus Ts1. The reason we can't apply this, right, is because we don't know Ts2 or C1. But if we make the substitution in here, we've essentially traded out this unknown Ts2 for C1, which is already here, and Ts1, which is known. So we've eliminated one of the unknowns from our equation down here. And we can write this now as H C1L plus Ts1 minus T infinity 2. So I'm going to go ahead and carry this over. So we've got, from the last slide, we'll go ahead and repeat that. We've got negative K C1 equal to H C1L plus Ts1 minus T infinity 2. Solving for C1, negative H over K C1L plus Ts1 minus T infinity 2. If we bring this C1 out, we end up with C1 plus C1H L over K equal to negative H Ts1 minus T infinity 2 over K. And then finally, if we were to go through the algebra here, which I'll spare you guys, we'd end up with C1 is equal to negative H over K plus HL Ts1 minus T infinity 2. Which leads us to the particular solution. T is equal to negative H Ts1 minus T infinity 2. Oops. K plus HL X plus TS1. So this is the solution for the temperature distribution across a one-dimensional plane wall. Again, if it's steady, there's no heat generation, and you have convective cooling on one side. Going ahead and plugging in heat flux and heat rate. Let's go ahead and Q prime X is equal to K H over K plus HL TS1 minus T infinity 2. Note that once again, the heat flux rate is constant across the wall, which means that once again our temperature variation is linear. Although we could have seen that by looking at our solution right over here. So the temperature variation is still linear within the interior of the wall. What changes is that now is how we got this TS2, because this TS2 is the product of this convective cooling occurring between here and the wall. So constant rate of heat flow through the wall, but we use that knowledge about that heat flow out of the wall and the fact that it's dumped into convective cooling here to a temperature of known fluid, or to a fluid of known temperature, in order to solve for TS2. Oops. And so the net heat rate in the x direction is going to be, once again, A times KH over K plus HL TS1 minus T infinity 2. And I want to take just a moment. So this, right, a lot of this just seems like it's a lot of throwing around of unnecessarily complicated expressions to get constant values, right? This is a perfect example of why in a few lectures we're going to get into this thing called resistance networks. The idea here is, right, you've all taken circuits, right, at this point, that the electrical resistance of some component, right, gives you the relationship between the voltage across that component and the current flowing through it. Same idea here, okay, but instead of electricity, we're talking thermal energy. If we were to say the voltage, instead of voltage, we're talking about a temperature difference, right? A temperature jump across some object, and we're considering, in this case, Q to be the amount of flow through that object. Instead of current, we're talking about thermal energy. Then this quantity here, okay, becomes what's known as the inverse thermal resistance. Right? It's almost directly analogous to the way we deal with electrical circuits. And so the whole topic of resistance networks is going to be, fine, how do we represent the equivalent resistance, or R value, of, for example, a wall with conductive cooling, a wall with convective cooling, a wall with radiative cooling, a series of walls stacked up together, okay? And to compute the heat flux or the heat rate through those walls, you just add up their respective resistances, and then divide the total temperature drop by that resistance to get the heat flow. But we're going to loop back around to some of these same problems with that mentality in a couple of lectures. So first, to kind of ground this thing, let's plug in a couple of realistic numbers into these results to give us some perspective. So let's say we were considering TS1 to be equal to 100 degrees Celsius. Maybe, I don't know, let's say that this is the wall of a pot that's containing boiling water. Okay. So when you have a boiling liquid on this side, in general, that fixes the surface temperature in contact with the liquid at that boiling point. So a boiling liquid is a really good example of a case when you have a known temperature condition on one wall. And then the opposite side of that, right, across the thickness of that, the wall of that pot, is going to be cooling by convection to the air surrounding pot. So say that T infinity 2 is equal to 20 degrees C, and H is equal to 10 watts per meter squared Kelvin. So these are typical of air at, sort of a warmish room temperature. And then finally, we need a thermal conductivity. Let's go ahead and say K is equal to 400 watts per meter Kelvin, which is typical of copper. So we're cooking in high-end cookware. So plug in these numbers in. Oh, good. All we end up with Q double prime X. I had these written out ahead of time, but I didn't bring it with me, so we're going to calculate these on the fly. Is equal to, well, let's compute C1 first, actually. C1's the ticket to everything. So C1 is going to be equal to negative H over K plus HL TS1 minus T infinity 2. Oh, and I wanted to say that L in this case is equal to, say, 0.001 meter. Okay. So that's about a millimeter thick. And so this is going to be equal to 10 watts per meter squared Kelvin over 400 watts per meter Kelvin plus that 10 times 0.001 watts per meter Kelvin times, we've got a jump from inside pot to the air outside of 80 degrees Celsius or 80 Kelvin. So end up with 10 over, let's see, 400 plus 0.800, and this is going to work out to be almost exactly 2 Kelvin. I'm missing a 0.1. Yeah. Per meter. Okay. So there's our so 2 Kelvin per meter. That's our temperature gradient, right? That's the slope of our temperature distribution. Yeah. Should it be negative? That should be, yes. That is going to be a negative number.
because that needs to be a, oh, yep, because the negative sign right here, so negative.
All right, a negative 2 Kelvin per meter. So there's our C1. Notice that this term right here, right, is our C1, and our Q prime X there is actually just equal to C1. So by finding our C1, we've essentially opened up our ability to solve for both Q prime X and QX. So if we were to multiply this by K, okay, by our thermal conductivity, I'm running out of space here, but so if we were to look for Q double prime X would equal to, or would be equal to negative K times this 2 Kelvin per meter, which would work out to be about 400 watts per meter Kelvin times that 2 Kelvin per meter. It's going to be about about positive 800 watts per meter squared. So let's say if we were to consider a typical cook pot you might boil water in. Say it has a surface area of, I don't know, if it's about 0.3 meters tall, probably got a diameter about the same. Let's say that's got a surface area of, I don't know, 0.3 square meters. That's a really big cook pot, but then in that case, the total rate of heat flux through the walls would be equal to 0.3 times 800 watts per meter squared, so about about 240 watts. So that's actually a lot of power, right? That's the idea, is that the dissipation of heat from boiling pot of water to the surrounding air is going to approach nearly a third of a horsepower, right? In terms of net wattage. All right. Let's. All right. One more quick one, and we'll pick up the heat generation in the next lecture. So this one's sort of a little bit dull once we get to it. But what if we were to take? Right, we've got our convective heat transfer going on this face, and on this face we have a perfectly insulated wall. Right. That which is known as an adiabatic wall. Remember, adiabatic from your thermo days means there's no heat transfer. Okay, so it's equivalent to saying that the insulation is doing its thing 100%. Okay, so in this case, once again, nothing on the inside of the wall has changed. We're still assuming it's one-dimensional. There's no heat generation. It's steady state. Okay. So our governing equation is once again going to be our k d squared t dx squared equal to 0. So the general solution is again going to be t is equal to c1x plus c2. But our boundary conditions have again changed. So we still have that heat flux boundary condition on this face, okay, saying that the heat flux due to conduction has to be equal to the heat flux due to convection. But what about on the insulated face? Okay. The idea is the perfect insulation, that adiabatic surface, means that there's no heat transfer, meaning the heat flux across that face has to be equal to 0. Right? So at x equals 0, we've got q prime x equals 0.
where that is equal to then negative k dt dx,
right? Fourier's law for conduction, but what we're saying is that Fourier be damned, we're not getting any heat across this boundary. And it's not because the thermal conductivity is 0, right? That's something inherent to the material. It's because
what it's saying is that at this boundary,
the slope of our temperature distribution has to be equal to 0. In other words, our temperature distribution has to be flat where it meets this wall. Okay.
Which tells us that C1 is equal to 0. If we go ahead and plug this into our general equation, we already see that this essentially means that T has to be equal to a constant, C2. All right. How about on the right-hand face, right, on surface 2? Well, at x equals 0, once again, there are any number of ways we could approach this, but, at x equals L, we've got that Q prime due to conduction is equal to Q prime due to convection, or that negative K dt dx is equal to H Ts2 minus T infinity 2. But we have, for this term, right, that this is equal to
0, because right here.
Which means that
Ts2 has to equal T infinity 2.
2 has to equal T infinity 2, and therefore we end up with C2 must be equal to T infinity 2 as well.
So in the end, all this tells us, our particular solution is that T is just equal to T infinity 2, which makes sense, right? The idea is if you insulate one side, you're preventing any thermal energy from entering. And so this part of the wall is eventually going to reach thermal equilibrium with the fluid on the other side. So it's going to all cool down until it reaches a constant temperature. We could have gotten to the same, we could have arrived at the same conclusion by applying the first law in Fourier's law, right? We'd say that if this wall is completely off limits to any thermal energy entering, then if it's at steady state, that means that no thermal energy can leave through this boundary, right? Well, if no thermal energy is leaving across this boundary, then that has to mean that convective cooling has been brought to a stop, which only happens if the fluid and the solid are at the same temperature. So, in the next lecture, we're going to talk about what happens when you have some rate of heat generation inside of the wall. So, in prep for that, please finish reading 3.1 and 3.5. And we're going to keep on going with the one-dimensional conduction equations on Wednesday.